Microsoft, and he's going to talk about Orbformer.
Thanks very much. Yeah, thanks so much for the invitation. I'm very, very happy to be here. Yeah, so I'll be talking about an ab initio foundation model of wave functions that accurately describes chemical bond breaking. Yeah, feel free to jump in with questions at any point as well. That would be great. So let me just start quickly with who are we and what are we working on, within Microsoft in this area. So yeah, I'm Adam. I was trained in machine learning, Bayesian machine learning, in my PhD. Then I joined Microsoft and started working with Jan and Frank on VMC, neural network wave functions and such like, along with Sherry, Bernard, Zeno, and at some point Jonas, Nick, Jarway, and Gino. So you invited an industry researcher, so here's an org chart for you, but this is the last one you'll see, no worries. So I'm part of Microsoft Research AI for Science, where we've got an initiative on VMC, we've got an initiative on DFT, and a number of other things, materials, proteins, for example. Then completely separate to us, we have another department working on quantum computers and stuff like that. So I just wanted to give you an idea of where we fit into that. But anyway, let's talk about science. So the setting for this talk is electronic structure theory. And in many ways, electronic structure is having a great moment right now as kind of the workhorse producing a lot of training data for all these, force field models, property prediction models, and so on. It has this unparalleled predictive power, and it's kind of the only non-statistical source beyond experimental data, right, for a number of phenomena. And, as was kind of nicely described in the last talk, DFT, which is a model based on the electron density, is really the kind of de facto standard method here. But it has this kind of annoying requirement of this exchange correlation functional. So in this talk, I'm talking about VMC with neural networks. So that's a full wave function method. And, lovely math. Very, very, very interesting method. It's not currently the de facto standard, really, for any application due to cost and scalability. And that's what we wanted to try and slowly put a dent into with this project. And it has one amazing silver lining, which is that there is no functional. You train directly by energy minimization. So it has this simple, unsupervised training principle. So I want to kind of break down the objectives, the why of this project a little bit. So where I think we're going with this research direction is, can we train an AI model that understands the electronic wave function at a fundamental level? And what does that mean exactly? I think that means that we need to be able to generalize across different molecules, or more generally across different Hamiltonians, a single model that can generalize between systems. That is obviously an extremely tough task, but I think that is sort of the ambition. And in many ways, if you look at the way AI research has developed, this is a very, very promising problem, because this variational principle gives us a completely data-free, completely unsupervised way to improve and iterate on our model. And we're only bottlenecked by what we can compute. And if you were to show that to, linguists or something 5-10 years ago, that was kind of the exact same promise that enabled large language models to be developed. Now, obviously, there are some caveats when it comes to wave function models, but I think the general principle and the vision is that we could train this sort of foundational model for wave functions.
Are you talking about ground states, or?
Talking about what?
Ground states?
Yeah, so I'll get on more specifically to what we did in this paper. I think in the big vision, there's no reason you couldn't do excited states as well. And people have done excited states with VMC. In this paper, we're looking at ground state, yeah. But then there was kind of a second objective for us, which is, could an improved VMC model for molecules solve something practical now that isn't better solved by an alternative method? And we identified multi-reference or strongly correlated systems as sort of the most promising place where VMC, if made cheaper, could be could be the method to go to. So if we could address some of these strongly correlated problems, specifically in sort of molecular bond breaking at a reasonable cost, that would be a big waypoint to say that VMC has a future as a competitive method in electronic structure. And just to kind of dig into that a bit more specifically, so in a typical molecule, if you start breaking bonds, distorting the geometry away from the equilibrium, you will enter a strongly correlated regime of the electron state. And existing methods that go beyond DFT accuracy, I think it's fair to say have a questionable reliability. So in this plot, we looked at CASPT2, and we looked at a simple scan across the reaction coordinate, and you find these sort of horrible, unphysical jumps in the energy surface. And often a lot of time, a lot of skill is required to make these sort of multi-reference methods work. And we already know that VMC with neural networks is a promising solution for the multi-reference problem in bond breaking. And computational cost really is kind of the main issue. So yeah, just to recap, our big vision is that we could build this foundational model of electron wave functions. And in the short term, we'd like to do something around this multi-reference problem. So now let's talk a bit about the actual methods and techniques. So I guess I'm preaching to the choir here, but we're looking at the time-independent Schrödinger equation, which through the Rayleigh principle can be recast as a variational minimization problem when you're looking, as you said, for the ground state wave function. The only constraint you have to put on is the anti-symmetry of your wave function. So this is essentially the basis of VMC, and this is kind of this very simple principle that I was appealing to before. We just need to solve a minimization problem. We don't need labels. We don't need an explicit training data set. So as an AI researcher, I look at this and say, this is ideal, an unsupervised problem where the equations of physics themselves describe an optimization problem that needs to be solved. Now, typically, when people apply neural network VMC in this kind of setting, you start training a new neural network for every molecule or for every different Hamiltonian that you want to consider. So, if you're given this configuration of the nuclei geometry, you would start training a fresh network from scratch, converge that. This would give you a wave function and an energy value. Then for the next system, you kind of throw that out and you start again with a new network. Now, that is a big source of this kind of unaffordability or like serious cost problem that we have with using VMC compared to your DFT or something similar. So what we wanted to explore in this project with Orbformer is how to do chemical generalization. So could we develop one model that would take in both the molecular configuration and, well, we'll see also the electron coordinates as inputs? We could apply pre-training to this model across many different molecules. And then at inference time, we would just do a small amount of fine-tuning on our target system and arrive at the required wave functions. And that is, I think the step towards this foundational model that I was talking about at the beginning is a model that kind of looks like that. Okay, so what is a chemically transferable ansatz? Like, how would we create or design one? So we start with, obviously, the molecules. Those are going to be our first level of inputs, and then the outputs would be the wave functions. And the wave functions, obviously, themselves are functions. So we'll work in a first quantized real space wave function land. So we'll take, actually, the two inputs now to our network are the molecular configuration and then the electron coordinates. And the output now should be the value of the wave function, conditional on that molecule for the given locations of the electrons. I haven't put in the spin here, but that is also present.
Are you going to assume a specific geometry for the molecule that you know the bond length, the angle?
No, that's encoded in M. So M is essentially.
You would learn angle.
No. We wouldn't learn M. So M would be an input. So we want to solve this problem for every possible value of M, or for a certain training distribution. I guess this is actually kind of on the next slide. So we will set up a training distribution over molecules, which includes a geometry, and that will kind of describe the space that we want this model to generalize over. And then if you the reason I put it with a vertical bar is it's a bit like a conditional distribution, right? So once you set that molecule and its geometry, now you want the model with that input on the molecule to operate as if it was the wave function conditioned on that Hamiltonian. Does that make sense?
How does the model know what geometry is unphysical?
What does it mean by unphysical? It just means that it's a very high energy state of the electrons, right? So we would like to admit those high energy states and model those as well. Because those are some of the most challenging, right? If you stick to your equilibrium geometry, then coupled cluster has basically already solved the problem. So, yeah.
So, presumably M is a set of nuclear coordinates and atomic type.
Yeah. In our setup, and this does miss some subtleties like different spin states and stuff. So we've adopted a slight simplification of the problem. But in our simplification, it's basically a list of the species of the nucleus and its position.
So then this construction doesn't guarantee rotation invariance the position of the nucleus.
No. So I'll get onto that in a later slide. But actually, you can't have that. So the wave functions actually can't be assumed to have the same symmetry group as the molecule itself. So the simplest example is the boron atom, where you have to break the symmetry in the wave function. So obviously the symmetry group of the atom is it's the symmetry group of a point, but the wave function, if you pick one ground state wave function, will have broken that symmetry. So you can't trivially put in the same rotation equivariance. So I'll kind of discuss this on a later slide, but we just didn't bother. Like, we didn't put any special treatment of rotation into this model. Yeah, but it's a good question, and I'll talk a lot more about like constraints we wanted to put on the model. So yeah, I think this is a key slide, so it's worth talking about this one. We're going to sample molecules from a distribution that we'll define, and it's meant to sort of show the model, this is where we want you to generalize in molecular space.
So could you clarify the form of the wave function? Is it expanded in an atomic data set or expressed on a real space array?
I'll show you that in 2 slides, so if you don't mind. And then ask me again if I didn't kind of capture the details. It's based on Slater determinants. So we're going to sample molecules from a training distribution we specify. But then in the standard VMC approach, we'll sample the electron positions using the current model, using Langevin MCMC. So that second part is what you would normally do in neural network VMC, but now we've just added this new level of complexity with the molecules as well. So I think everyone would agree, if you want to do generalization, you need some level of scale in your data. And this is a kind of a very limited summary of previous neural network VMC approaches. And the biggest one, so this paper from Vienna, they did a very simple version of this pre-training idea. They pre-trained on 360 different molecules, up to 22 electrons in equilibrium distribution, and then they showed that did indeed give them a benefit at fine-tuning time. But in this paper, we want, also, we're at Microsoft, we have some GPUs, so could we go bigger, right? How could we scale up beyond like 360 molecules? And achieving this level of scaling requires some quite serious changes to the methodology, the architecture, and so on. So first of all, we need a new architecture to handle this dependence on the molecule. And we also need to think about how we converge our Langevin MCMC. And then there's some kind of side things which I won't mention in the talk, just for time. We need to think about the Laplacian. We need to think about how we're going to handle multiple determinants. We need to think about, well, what do we actually put into our pre-training data set? And a completely other side topic is, could we take out the electron density once we've actually trained this? So I'm happy to talk about any of those afterwards, by the way, but I didn't put them in the talk just because of time. Okay, so now we're getting onto the architecture. Hopefully this will answer the question. So it's a pretty standard setup, right? So we have a Jastrow factor, we have a sum of like generalized slated determinants. This gives us the anti-symmetry property that we need. And okay, so in this talk and in our paper, I'm going to use the word orbital in a slightly like abstracted sense. So for us, an orbital is any permutation equivariant function of the electrons, right? So this includes, and you'll see that we use self-attention here, for example. So anything with backflow is allowed because it's permutation equivariant. Obviously, classic single electron orbitals would also satisfy this, but we use self-attention.
Just a suggestion. It's not quite a slated determinant. It's really beyond slated.
Yeah.
Determinant, but it's beyond slated.
Yeah, you're right. It's not really a slated determinant anymore. It's just a determinant. Okay, so this is a bit more of a deep dive into this architecture. So yeah, we have these two inputs, right? Electrons and molecules. We have our Jastrow factor, and then these generalized orbitals are made as a direct product of two things. So one is an envelope, and these are like very simple functions, similar to like S-type orbitals in quantum chemistry, and they control just the general placement of the orbital, general localization. And that picture shows you what they typically look like. So they kind of highlight a certain area in space, but they don't really contain that much information. And then the electron transformer representations are doing kind of the heavy work. So this is quite similar to an earlier talk that we had yesterday, where they also looked at using self-attention within a neural network ANSYS. And in some ways, it's like the perfect architecture, right? Because it is permutation equivariant by design. So it's the exact property that you would want. And we've found that it's always just been kind of the best solution for us so far. And essentially, just to give you a general idea of how we deal with the molecules, so these molecular coordinates are passed through their own kind of separate network, and from that, a series of weight matrices are produced. And these weight matrices are how we depend then on the molecule. So that's kind of the way transferability is achieved so far. I think there's definitely space to do more here and control more aspects of the underlying wave function using in a way that's molecule dependent.
Question?
Yes, please.
So what's the role of the Jastrow factor? Because it seems like you can assign all the complexity to the transform.
Yeah, so our Jastrow factor is super simple. It just does the electron-electron cusps. So it gets the exact cusp condition on the electron-electron sort of, as electrons become very close.
You move that to the transformer part?
Maybe, but since we know it's so cheap, the Jastrow we have is super cheap and super simple, and it exactly solves the cusp condition. So we might as well just keep it, I guess. That's my answer. And you notice it's not transferable, right? Because it's just doing the electron-electron cusp, so it doesn't really need to depend on the molecule itself. So yeah, potentially you could put it into a transformer, but I think it's so simple we might as well keep it in the Jastrow. So that's effectively learned. So the way you depend on the electron nuclear distance, it doesn't have a zero gradient at zero, so that there exists essentially a cusp term which can then be transformed and can give you essentially the correct limit for the electron nuclear cusp. Yeah. Yeah, go ahead. What's the biggest bottleneck? I think I think the biggest thing I would change about this is how we deal with the molecule, because I think that is still, this is super new. That's very much up for grabs. I would like to put molecular information just deeper into this architecture. So I think in terms of generalization, that is what I would change. In terms of speed, like where's the compute going? It's really going in the Laplacian, and the Laplacian, I guess, it's just basically every time you have a linear layer, that's a relatively high cost. I don't know. Does that answer your question? Yeah. Okay. Thanks. Okay. So again, something we've heard quite a bit about in this conference is that you need to put in good constraints to your networks, right? If you want them to sort of respect physics and respect the problem. So what constraints should we put in to this network? So permutations of electrons is essential, right? Otherwise it's not fermionic. So we have that via the determinant. Permutation of the nuclei, that is handled. So essentially that just leads to a sort of reordering of the orbitals, but otherwise the same physical wave function is maintained. Translation invariance, yes, we have this by just only ever looking at relative positions between two particles. Rotation invariance, right, so we did briefly discuss this. So it's not valid to have the entire model be rotationally invariant because certain wave functions have to break symmetry. So we just applied rotation augmentation to the molecules. So you just show it molecules in different rotations, and then you just leave it to the model to figure out, okay, how am I going to break symmetry in different cases? Yeah, there could also be sort of interesting work done on how exactly to characterize the symmetry breaking, but I guess we just didn't look at that specifically in this paper. Okay, so we put all of this in. Was there anything else to add? And yes, there was one kind of big constraint that we found really helped, and we referred to this as composability. So this is something that's sort of related to localization and size consistency. And the way I describe this constraint is to say, if you have two copies of the same molecule that are separated by an infinite distance, then the kind of Slater matrix, or the matrix that you're going to take the determinant of, should have this form. So it should have two exact copies on the diagonals, the sort of leading diagonal, and then zeros on the off diagonals. And this is something that we wanted to enforce as a hard constraint. And the reason we wanted to think about this as a constraint to bake in was we wanted to somehow learn features in small molecules which could be applied in big molecules. And we thought that size consistency is kind of the limiting example of that behavior. So if we could get size consistency baked in, or something that's similar to size consistency baked in, then that could be a good starting point for learning generalizable features. So how did we get this composability thing in? Essentially, it just boiled down to a kind of tweak of layers that we're already familiar with. So for example, electron-electron attention layer doesn't naively work in this way. If you add a distance bias that is forced to decay with large distance, then you do get composability in this layer. If you look at the interactions between electrons in every nucleus, right, the standard way to deal with this is you just literally just stack all of those features together. That doesn't really work, and it's not composable. So instead, we did a kind of summation based on distance in a way that the weights would decay to zero in the infinite distance limit. And also, we got rid of Hartree-Fock, finally. I feel like Hartree-Fock has been sticking around in VMC for such a long time as an initialization. Hartree-Fock, by default, is not localized. It's just completely delocalized if you run Hartree-Fock calculation. So we got rid of that, and we just did a much simpler initialization based on some kind of local charge balancing, which is not as good of a model, but it's a better starting point if you want to train something that will be composable like this.
Question?
Yes.
So this desire to have composability seems ideal if you want to consider some larger molecules made of smaller pieces of molecules.
Yeah, exactly.
But it seems not, it does not, to me, it does not look like a way to understand crystals.
Yeah,
So it's like totally different direction. Like it's not, it doesn't seem to be a good starting point to try to study solids.
we've not applied this to solids, and I think if you wanted to do solids, you should probably like.
You need something very different.
Yeah, I agree. I think you want to think about. I know a couple of works have looked at VMC for solids, right, and I think they've used quite different techniques. For example, like periodic envelopes rather than sort of location-based envelopes. I completely agree. I think solids have a different character that would require some different constraints.
Wait, but I thought for solids, the equivalent of what you're doing would be to break a solid apart, make it not as big.
Yeah, but if you can, if you think about NaCl, what are the molecules that you put together to make NaCl crystal, right? So this approach, like this is a great approach if you want to understand how you get a larger molecule out of a smaller molecule. When you have some sort of basis, pieces that often come together, maybe like even organic chemistry, but like thinking about larger molecules, I think this is a great approach. But I don't see how this would be the best starting point, effective, efficient starting point for understanding solids.
Obviously, I shouldn't speak for the speaker, but the chemistry concept of sizes tends to be just being if you break two pieces apart, that's only two plus. And that principle of science is important that you follow it. You want to scale it
Yeah, thanks. I think it's a really interesting discussion. Would be keen to follow up afterwards. But just to kind of emphasize, we focus on molecules in this paper, and so that's why we kind of focused on this constraint. The pre-training data set that we made was of slightly over 22,000 structures, so a lot more than, I think you saw the previous effort went up to 360 molecules. And we included a lot of, kind of broken bonds and more of these like high energy geometries that we wanted the model to try and learn from. We included, data augmentation. We also took this kind of curriculum learning approach, which we found made the training more stable. So you start teaching the model kind of easy stuff, and then you add harder geometries later.
Exactly what are the training data? Are these the energy and the wavefunctions for certain molecular configurations?
So it's just the molecular configuration, right? So this is kind of the great point, right? Is that it's unsupervised. You just show it the molecules you want it to train on, and then you apply the variational principle. So it's just choosing the molecular geometries that you want to put into the model. And what's that, sorry?
Energy minimization.
Yeah, and then so then conditional on your training data set, you try and minimize the average energy across all of the different configurations. Yeah. And one kind of other final note on the methodology, right? So we're going to keep changing the molecule that we're looking at every step. So how do we deal with the Langevin convergence, right? Burning in these Langevin chains takes a long time. And we worked on this problem for a long time and eventually came up with a very simple solution. So what people typically do is they use MALA, right? Metropolis Adjusted Langevin Algorithm, which has this accept reject step. And what we did was we just used unrestricted Langevin. So just always accept proposal, use that as an initial equilibration, then just switch on the Metropolis adjustment in the second half or something. And the improvement, so if you look at the middle panel on the right-hand side, this is some like distant statistics of the electron sample, and you can see that this Euler version converges, so much faster. So this was a problem we worked on for a long time and just ended up with this very simple solution. And this helped quite a lot. And then, okay, final thing to say is, so we didn't converge the wave functions on the entire pre-training data set. That's kind of, but what we did was we arrived at a much better starting point. What we did find was that you could put very similar structures together and fine-tune them. So you could put molecules in batches of, say, 20 or 50 similar molecules, and you could fine-tune them to convergence, and you could squeeze out quite a big cost saving there as well. So you've got this better initialization from pre-training, and then you've got this sort of joint fine-tuning. And when you put all that together, you might get a factor of about 50 compared to just training everything from scratch again and again. Okay. Let me just quickly go over the results then. So we looked at relative energies as our sort of metric because chemists told us we don't care about total energy. No one cares about total energy. Relative energy is where it matters. And the reference energies we used, reference energy is hard in VNC because it's so accurate. So you need something that's even more accurate. And you'll see a variety of different references used. So the first one was experimental references in this Diels-Alder reaction. And you can see, so Orbformer is kind of like these bottom two panels. And you can see, first of all, the pre-training helps. So you just generally get lower error. And it systematically converges to the right answer. If you use something like DFT or CASPT2, right, you would think a bigger basis would be better. But actually, pretty much always bigger basis was worse for this problem. So they require a lot of this like hand tweaking, which is very annoying. VMC just sort of converges. And this is also a challenging problem with this multi-reference transition state and stuff. So this was a good check against the experiment. And then here, we wanted to benchmark on like these very dense reaction profiles. So here we used basically expensive single point VMC as the reference. And then what we compared, Orbformer from scratch, Orbformer with pre-training, and then Orbformer with this kind of joint fine-tuning and everything. And this was kind of the, maybe the result we were looking for, which is that this dark line is pretty much always, on the Pareto frontier, so the sort of bottom left compared to like the family of DFTs, MRCCs, and so on. So it's pretty much now sitting at the Pareto frontier between cost, which is the x-axis, and error, which is the y-axis. So for any given cost, you get about the best accuracy that you can compared to competing methods, and you systematically converge below chemical accuracy. I'll just skip this because of the time. And the final thing we looked at was like interpretability, and we looked at the kind of localization of the orbitals. And the interesting thing we found here was that without this being encoded in the model, Orbformer proposes exactly 2 totally localized orbitals for every carbon atom. So these are like your classic core orbitals that you would learn about in high school chemistry. But this just drops out of the variational principle, right? No one coded this in. No one hard-coded the existence of it being 2 out of 6 core orbitals. So that was kind of a nice win for getting a really interpretable result just directly from this sort of pre-training using the variational principle. So yeah, thanks very much for listening.
Any questions?
I just had a question about the scaling that you showed on class, the bundle book.
Yeah.
Yeah, this one. So here, to me, it looks like the lines from the different Orbformers are actually about to intersect. So it's maybe not the y-intercept that matters, but the exponent. So, does that make sense?
Yeah.
So then, if our compute access improves, why wouldn't we just get the most accurate thing by increasing the compute and taking then the lowest line?
Yeah, for sure. I mean, I think a lot of people say VMC is too expensive, right? So I think it is worth seeing if you can get better performance at a lower compute. And clearly the pre-training helps. So yeah, the fact that these 2 lines intersect basically says that if you've fine-tuned for 200,000 steps, the effect of the pre-training is kind of worn off, right? Because you've done so much specific training on this specific system, which is kind of, I suppose, what you would expect. On the other hand, if you're not willing to do much fine-tuning, the pre-training helps a lot. So that's kind of the point of those two lines. Now you make a fair point. If you want to just burn GPU hours and you're kind of willing to just spend the money to go to convergence, then maybe the pre-training isn't really helping you on these bigger systems. I mean, it's clearly, on ethane, it clearly is still helping you, right, at convergence. It's got you a lot faster. I think, a better model, Orbformer version 2 or whatever, you'd see the benefit of pre-training lasting longer. So indeed, that is something we'd love to see. But for these systems, as you reach chemical accuracy, the benefit of pre-training is, between the ethane curve, propanol curve, there's still some benefits. L-alanine, there's not really any benefit left at the 1 kcal per mole level. Yeah.
Could you explain the data on the previous slide in a little bit more detail?
This one.
Yeah.
Yeah.
So this activation energy error,
So there is an activation energy from the experimental paper that we looked at that's like corrected for 0-point vibrational energy, etc. And then we just evaluate the activation energy using all of these methods. Okay, there is a subtle point, which is that we take a transition state geometry that was also sort of previously found in an earlier paper. So we just compute the energy difference between those two states. Yeah.
Okay. Thanks.
Might be a somewhat naive question, but all the constraints that you seem to put in,
Yeah.
translation variance and swarming, and even the composability, seems like stuff that could be done by just data augmentation without having to constrain your model, because you have enough, seems like you have enough pre-training data. Why would you, and my current understanding is that having a general model set seems to have better performance than putting in biases.
Yeah, this is like an age-old debate, and definitely in machine learning. Do we need equivariance at all? I think so. For us, I didn't discuss this just due to time, but we didn't train on very, very big molecules. So I think the biggest molecule, I can't remember. I think it was about 24 electrons, but the test systems went up to 106 electrons. So the hope was that you do all of your work where it's cheap on the small molecules, and then you can kind of save time on the big molecule where gradient steps are very expensive. Now, for that to work, you probably do want some kind of composability. Yeah.
In your approach, you sample over unibody weight function, is there a method guarantee that this is a complete representation principle of a dysmetric wave function, or are there some possibilities that may be missing?
So you mean is the true wave function necessarily within the space of our model? No. It's a finitely parameterized model. So I think the answer is definitely no. But it seems that we can usually find good enough models. The only one thing I would say. Okay. First of all, you could use this just on a single system, right? Forgetting about this transferability generalization. In which case, it's still finitely parameterizable, so you still don't have a guarantee of the exact function being in the class, but you think that one is very, very close. Then you could ask another question. It's like, okay, if you're generalizing over input molecules, does that somehow weaken your position further, so that it's now even harder to find a good fit? I think that's probably true. And I think there's definitely more work to be done on how do we enable the right amount of flexibility to get into the model. I think our kind of saving grace is that we fine tune. So then you kind of get back to essentially the single geometry version, which is more well accepted. Does that kind of answer the question?
Yeah, just whether in principle.
Yeah.
Given enough of these general determinants, could you arbitrarily approximate, or is it?
Yeah, I think it's like an interesting mathematical question, right? Like, does there exist a transferable model which can provably represent the space of wave functions. To which I would have to say I don't know, but it's a very interesting question.
To answer your question, of course, if you use exponentially large number of stated determinants or determinants, then universal representation part is guaranteed. So the real interesting question is, if you use a finite or polynomial large number of determinants, for example, generalized determinants, is it enough? Now, turn out for this approach, the practical determinant approach, at this point, there's no understanding whether that is sufficient or not for normal numbers. But there are other architectures, other approaches that guarantee universal representation. I can tell you.
Thank you for the great talk. One question I had was, have you looked into the hierarchy of transferability of the weights of your, foundational model? So, are the first two layers the ones that generalize better, or the later layers, do the job of fine-tuning the molecule?
Yeah, great question. I think definitely these envelopes are doing a lot of work. One thing we did look at is, this thing I showed you about the core orbitals. When does that arise? And we showed actually that arises within the first 5% of the time spent on training. So I think the orbitals, the orbital envelopes are doing a lot of this work on generalization. Sort of basically, how do you roughly pack in all the electrons? And I would then think the transformer is probably doing a bit more of the specific tuning, and I think that's probably the thing that is not maybe transferable to the same level right now.
Interesting. So you don't see any hierarchy that the first few layers are more or less the same for all the molecules, but the final layers are more specialized to particular cases. So it's more or less in average 5% or so.
Yeah, so I didn't break it down by that. I kind of broke it down by this. So the envelope versus the transform representation, and then looked at as you fine tune. Say you've started from the same pre-trained point, and then you're going to fine tune, and they're going to diverge. Where's the divergence? And it does seem like the divergence is stronger on the transformer representation. Yeah.
Thank you.
And how do you optimize this nuance? Is that weighted time?
Yeah, so we use KFAC, which is kind of become one of the standards. So yeah, we didn't. There's no real innovation there. I think we did kind of what people the standard approach that people would use in this.
So, let's have one last question.
So, when you try to do that, you're especially aiming for touching that right excitation and these more consequence. So I was wondering, so basically you're looking to train an experimental cell. So first thing you train is that you check because the truth of the result is physics informed by the training the environmental test.
Yeah, I think that's really interesting. So we didn't try that in this paper, but I think that would be really interesting. I mean, so one thing that people do is if you're looking at an energy difference, say between an excitation and a ground state, and you see that the local energy variance is much higher in one than the other, then you would try and correct for that. That's not in this paper. That's kind of an earlier work from colleagues. So that's something that you could do within the VMC framework, is that you try and variance match so that you get a better error cancellation, for example. Then, okay, could you do supervised learning with an observable? That's not something that we've looked at yet, or at least not in this paper. Yeah, thanks. Cheers.
But the bench time, so you move around, percent of the margin as well. Do you find it's better to bench, so smoothly walk across molecule geometries, or to bench with the reason to jump from one molecule to the other?
So yeah, that's an interesting point. So we don't smoothly transition between molecules. We just resample completely different, different set of atoms, different positions, totally different. And then we run this algorithm to kind of restart the electron samples. The thing that we did do that I only briefly touched on is this curriculum learning approach. So rather than just training on everything random sampled, we start with like very small things, so up to 10 electrons, and with kind of slightly more low energy geometries as well. But not with the smooth transition, which it might be interesting to look into. And then we kind of add harder and harder molecules as we go. Yeah, sorry. I hope everyone heard that without the microphone.
Okay, so let's
Thanks very much.
thank the speaker again for